So I've been watching the evolution of Clojure for quite a while, and I've been thoroughly impressed with the consistency and clarity of thought that Rich has brought to the goal of making software easier to build, maintain, and understand. And as Stuart said, this is a goal that I've also dedicated quite a bit of time and effort to, and who knows if either of us will be successful, but certainly I hope one of us is, because the state of software development today well leaves some room for improvement. Now, Rich has taken an approach that is advocated by the modern Greek writer Nikos Kazantzakis, who once said, "You have your brushes and your colors, so go paint paradise, and then in you go." And this is definitely a fun route, because you build exactly what you want, and if you're lucky, you gather a community of like-minded people around you as you go, like this community here. And I've chosen a slightly different approach, a more incremental approach, trying to pivot a larger existing community towards a better way to program, which is definitely slower going, but it also has a lot of leverage. So the way I look at it is, if I can help 9 million developers become even slightly better programmers, this really adds up to quite a big difference. So for purposes of today's talk, maybe you should pretend, or maybe you already do, that my title isn't Java Language Architect, but instead this. And today I'm going to talk a little bit about my experience piloting Java over the last few years and some ideas about where it might go next and some lessons that I've learned for the journey so far. As Stuart mentioned, a few years ago, I wrote a book on writing correct concurrent programs in Java, which is something that most people at the time thought was either trivial or impossible, and the key message of the book was that both of these views are woefully wrong. I remember at one point, Rich made an offhand comment that he created Clojure because he was tired of telling people to go read my book. So in the spirit of Al Gore having invented the internet, I'll just take a tiny little bit of credit for the inspiration behind Clojure. So I want to talk about pragmatism for a minute. Pragmatism is generally considered a good trait in engineers. So how many people here in this room consider themselves pragmatists? Warning, it's a trick question. Okay, so some people fell for the trick question. All right, so let's dig into what that means. So I understand the local custom is to ramble on about dictionary definitions for a while. So Webster says that pragmatism means a reasonable and logical way of doing things or thinking about problems that is based on dealing with specific situations instead of ideas and theories, or more succinctly, a practical approach to problems and affairs. So, well, that sounds pretty good. Who could be against having a practical approach to problems and affairs, right? So, okay, let's dig a little bit more. The American philosopher Charles Saunders Peirce, sometimes called the father of pragmatism, stated what is now called the pragmatic maxim in 1878, which is, consider what effects that might conceivably have practical bearings we conceive the object of our conception to have, then our conception of these effects is the whole of our conception of the object. Okay, that's a little wordy, and I know not all of you have philosophy backgrounds. So here comes the TLDR version in the voice of, well, if maybe not the words of, a better-known philosopher. There is no good. There is only good for. So what Master Yoda means here is that we need to look past our own aesthetic and principled beliefs and judge things on the basis of whether they work in the real world. So we should judge the good of something based not on its intrinsic properties, but on what it is good for. So some of you at this point are probably feeling a little bit tricked by my trick question of who here considers themselves a pragmatist, but too late to change your mind. We're already moving. Let's see where it goes. So one of the things that you can learn from the history of programming languages is that there's no perfect programming language. Now, this should be kind of obvious if you think about it, because even if there was, the sorts of problems we solve with computers change over time, and if the problem is changing, then the tool that might have been perfect for one set of problems is unlikely to be perfect for tomorrow's problems. So I prefer to take a more evolutionary view of programming languages and tools. And so the analogy goes like this. Imagine an ecosystem where the programming problems are the prey, the programming languages and the tool are the predators, and the state of computing hardware and infrastructure is the environment. So, okay, we've got an ecosystem. Now we let evolution do its thing. And we watch how the denizens of this environment is going to change over time. So if we view this through the pragmatic perspective, we should judge that programming languages aren't good and bad in and of themselves, but instead that language X may be good for certain kinds of problems and may not be good for other sorts of problems. And if that's a useful way to talk about things, then maybe we're better off, rather than talking about good or bad, talking about languages as being evolutionarily fit or not for the environment that they happen to find themselves in. And, continuing the analogy, some creatures that are evolutionarily fit for one environment manage to adapt and change as the environment changes, and others don't, and they die out. So I think this is a pretty useful way to look at programming languages. Now, evolutionarily fit doesn't mean pretty. It doesn't necessarily go the other way either, but there are certainly different kinds of ugly. There are some things that are ugly because their ugliness actually serves their evolutionary mission. I mean, think about the anteater or the naked mole rat, right? Those things are hideous, but they're very evolutionarily fit for their niche. And then there are things that are not ugly, but they're more like warts. They don't serve the evolutionary mission, but they don't interfere with it either. And in this ecosystem, mutations aren't really random. They're deliberate decisions made by designers. And so with benefit of hindsight, we might be able to judge certain decisions or features as being errors within their evolutionary context. So I went looking for a really good example of this, a programming language feature that ran completely counter to the language's true design center. And so I went looking for an example. I first tried the wisdom of crowds approach, so I asked my Twitter followers to name the most bizarre language feature that they could come up with. And I tried to be explicit about the criteria. I wanted bizarreness relative to the language's principles, rather than just the personal taste of the reader. You can imagine about how well this worked out. And so I was inundated with participation age blather like, oh, I can't stand that semicolons are required here in this language, and stuff like that. But what I was really looking for was an example of where a language designer had lost their way, where they had deliberately gone back on their principles to illustrate just how easy it is for short-term expediency to lead you into making a bad decision. So after Twitter proved useless, and answering the question that I actually wanted the answer to, I asked some smarter people, and of course, I got exactly the answer, the example that I wanted from Guy Steele. And there's a lot of lessons in this, but I'm going to move on. So at the risk of sounding like a 70-year-old Gary Bernhard, I don't know if Gary is here. Is he here? Okay, let's talk about COBOL. Okay, quiz time. How many people here think that COBOL sucks as a programming language? You always fall for the raise your hand trick. How many of you have written a program in COBOL? Wow, I'm impressed with that. Okay, so now remember, we're being pragmatists, right? So we shouldn't say COBOL sucks as a language. We should say whether it is good for or sucks for certain kinds of problems it might be called upon to solve. And in this evolutionary metaphor, COBOL was actually quite a fit predator indeed for the programming problems of the 1960s. And this makes sense if you think about it. The database technology at the time involved storing data on punch cards or magnetic tape that emulated punch cards. And the most common programming problems of the day were producing accounting statements and query reports like sales by salesman and region and things like that. And so a language built on imposing weak types on 80-column strings and doing that to a bunch of records that have been read in off some I/O device and doing some simple aggregation and spitting out some suitably formatted summary records was kind of just what the doctor ordered in 1960. While we're at it, I could note that Fortran was similarly evolutionarily fit for the programming problems of the 1950s, which were largely dominated by the production of artillery firing tables and things like that. So these languages that we like to look back on and maybe poke some fun on were actually, quite evolutionarily fit predators for the ecosystem of their day. So a little bit of a history lesson here. So the imperative part of a COBOL program was divided into paragraphs. So here we see a paragraph labeled foo-para, whose body does some simple computation. And control flow was accomplished by the usual suspects. You had vaguely stack-based subroutine calls and unconditional jumps to name targets. And this isn't beautiful, but it was what we had. And you could write reasonable enough programs with it. So, okay, here comes the bizarre part, as if talking about COBOL in 2014 wasn't bizarre enough. The alter statement. Does anybody know what the alter statement in COBOL does? Few language historians here, yes. So the alter statement is COBOL's self-modifying code feature. So this statement means change the jump target of the paragraph called foo-para to branch to baz-para instead. And of course, to make that make sense, it had to be the case that foo-para referred to a paragraph that had only one statement, and that was a go-to. So my claim, with no evidence whatsoever, was that this was COBOL's WAT moment. Okay, so we don't really care exactly when COBOL jumped the shark, but stuff like this actually keeps me up at night. Because COBOL, no, really, COBOL was a serious evolutionarily fit predator, for solving serious business problems in 1960. It had a reasonable set of organizing principles which might look primitive by today's standards, but they were the basis for an entire industry that really did accomplish amazing things. And then we discover stuff like this. And what's scary about this is some serious people with serious responsibility thought this was a good idea. And the lesson is, smart people can do some really dumb things when they're under pressure. And sometimes it's very hard to tell the brilliant compromises from the complete sellout of your principles until way too late. And I'd rather not be judged by history as the doofus who did this to Java, so stuff like this keeps me up at night. So, okay, let's talk about Java. Now, Java may not be the prettiest thing, but it still is the dominant predator in today's programming ecosystem. And I know you guys have a bit of a love-hate relationship with Java. On the one hand, you like and need the JVM and all the great services it provides. And on the other hand, the JVM wouldn't exist without the popularity of the Java language. And more precariously, the JVM's ongoing development is coupled to the ongoing development of the Java language, which might be a little bit scary for some of you. So my little story about COBOL jumping the shark was really a long-winded way of getting into the main theme of my talk today, which is stewardship. So what does this mean? A steward is somebody who has responsibility for maintaining property entrusted to them by its owner. And this is the word that I use when I describe how we approach evolving the Java platform. So coming back to our evolutionary view, stewardship means ensuring that the Java language and the JVM remain suited to the combination of programming problems and programming environments that we're going to find today and tomorrow, which may be different from what they were in 1995. Some people ask me, why do I even bother with such an old technology? I mean, I could be working on something much newer and cooler, right? And it does take a tremendous amount of effort to move something as big as Java. So why bother? And as I said earlier, there's a simple answer to that. That's leverage. Having your code running on 1 billion machines is leverage. Teaching 9 million developers to program even a little bit better has a huge aggregate effect on the world of programming, more than anything else I can imagine. Wouldn't it be great to teach 9 million developers that, say, side effects are overrated? Where else are you going to get that chance, right? So that's why I do what I do. One of the biggest questions that any community is going to grapple with is change. How much, how fast? The world changes, and we have to change with it, otherwise we risk becoming irrelevant. But we also need to evolve carefully because, in the context of our community, even the smallest change, could break someone's mission-critical code. So there are forces that push us in both directions. There's forces that push us towards more change, keeping up with the changing hardware reality, business problems, developer demographics, and even developer fashion, and also, of course, trying to fix some of the inevitable, mistakes that we've made in the past. On the other hand, there are some forces that resist change. We have a very low tolerance for making incompatible changes. And we don't want to buy into fashion of the week because that risks alienating the loyal users who kind of got us where we are, right? And they may like things reasonably well as things are, and there's always the possibility that we could end up making things worse rather than making them better. So these are forces that resist change. And just like in politics, the folks at the wheel are probably going to be hated from both sides, right? Because one group says you're not going far enough, and the other says you're going too far. So ignoring the fact that someone's going to hate you no matter what you do, any change you make is going to receive extensive scrutiny and second guessing. And this sucks, but it's better than the alternative, right? I mean, there's an old saying, there's two kinds of programming languages, the ones people complain about and the ones no one uses. So, one option, if you're, allergic to being complained at, is just do nothing. Throw up your hands, say, it's too hard to do anything. And you can get away with that for a long time. But this is kind of the cowardly route, right? So instead, what I think, you should do is adapt to the forces in play. So I posit that the rational counter-strategy in such a situation is to put more eggs in fewer baskets. The consequences of even a small change are surprisingly expensive to estimate and certainly easy to underestimate. You're probably better off investing in bigger changes that have more of a chance of a positive cost-benefit ratio. So this is actually something people in the Java community find incredibly frustrating because we seem to be unwilling to make seemingly minor changes or fix obvious mistakes. The reality is, with millions of users and billions of lines of outstanding code out there, there's no such thing as a minor change, and nothing is obvious. At some point, I realized that there's kind of a disconnect between what people think I do and what I actually do. I was chatting with one of the researchers at Oracle Labs, and he made this comment that he's always surprised to hear me describe my work. So I made some charts to illustrate the disconnect. So in his view, my job would mostly be about technical aspects of language design. It's a nice view. Don't take this away from him. You've got type theory and soundness proofs and adding features so we can express more kinds of programs safely and sensibly and make the intent of the program more clear. And totally reasonable academic view and probably does accurately describe the ongoing development of Haskell or ML. And don't get me wrong, these things are part of my job too. But what threw him is that what I actually talk about are the softer concepts that have more to do with user psychology than about type theory. So, I'm constantly saying things like, that's not where I want to spend my complexity budget, right? I have a limited budget for users adapting to new ideas, and I want to spend it where they're going to get the most payback. Or we might discard an idea on the basis purely of cultural constraints of, well, that's just not how Java developers think about it now. And these are concepts that come, if you're coming from an academic programming language background, you might think about. So, one day he said to me, he's like, all right, finally, I get it. You're not Enzo Ferrari, you're Henry Ford. Ferrari is all about building the best, fanciest, coolest car you could imagine, right? And if adding a new type of turbocharger or massage chair makes the car better, then that's what you do. But Henry Ford set out to build practical cars for ordinary people. So forget the turbocharger and the massage chair, but if you can improve the gas mileage or make the dashboard provide more useful information, that's a big win. The Honda Civic is a pretty fit predator in its ecosystem too, even if it's not as pretty as a Ferrari. So this chart's a little bit less charitable and therefore a lot more fun. And this is what I sometimes think people in my community imagine that I do based on what they say. If we go clockwise from 12 o'clock, you got your secret backroom meetings. Every once in a while, you poke your head out of the secret back room and make some self-important comments on a mailing list, right? And then maybe you come to a conference and make some more self-important comments. And from a technical perspective, it's mostly about stealing features from other languages and, of course, lots and lots of syntax bike sheds. And, it's fun to make fun of your users, but, and it's certainly therapeutic, but it's also important to remember that these are the people I'm doing this work for, right? So in some sense, success looks like not bursting their bubble about how it works. And just making it work better anyway. And James Gosling described Java as a blue-collar language. It's a tool for real programmers to get their work done. And there may be plenty of rocket science that goes into designing it or implementing it and certainly specifying it, but you shouldn't have to be a rocket scientist to use it. Now, this turns out to be kind of a difficult constraint, and to make it even harder, a wide-spectrum language really needs to have wide-spectrum users. Otherwise, you're going to lose sight of where the mainstream is going next year. So while Java may primarily have its home in server-side business logic, it really can't afford to alienate the more cutting-edge users like the high-frequency trading guys. All right, so this one looks a little bit closer to what it feels like I actually do. So, you definitely do have, the meetings and interactions on mailing lists and conferences, but the technical focus is really different. It's not as much about adding features as it is about keeping features out. If you look at some academic languages or some non-academic languages that I won't name, but whose name might be an abbreviation for scalable language, it seems like the goal is add every feature you can, right? But that's generally the last thing you want to do. Every feature adds some bad weight. Every feature might interact not only with every other feature you have, but every other feature you might want to add in the next 20 years. So every feature is one step closer to collapsing under the weight of your own complexity, like being Perl. So we have to choose very, very carefully. And when you do add features, there's a tremendous amount of work to fit them in with the existing features and to analyze and test for interactions with existing features, and not just existing ones, but future ones as well, and analyzing the compatibility consequence of everything. And of course, no feature analysis is complete without discovering just how badly it interacts with serialization, which is my favorite feature. So the really fun part is this one down here at the bottom, right? That's what would James do? I get to do that every once in a while. So as you can see, this is a somewhat more conservative view of language evolution. It's also the price of success. So I spend an awful lot of time thinking about compatibility. I mean, so much so that I spend time thinking about how to think about compatibility, because it comes in many forms. You know, you've got your binary compatibility, which is about whether call sites embedded in existing class files will continue to link. You've got source compatibility, which is about whether clients or subclasses will continue to compile. You've got behavioral compatibility, which means things continue to work in the same way. You've got serialization compatibility, which is about whether instances serialized on an older version or even a newer version will continue to deserialize properly. And then there's a whole bunch of more subtle compatibility issues, such as changes in performance characteristics. To make matters worse, there's actually a cross-cutting concern that's fundamental to all of this analysis, which is separate compilation. Because of dynamic linkage, every call site is linked at runtime nominally, and this is why you're able to just drop a new jar on the class path and keep going. You always have to deal with the possibility that only part of the system's been recompiled. And normally this isn't a problem, but this can show up when, for example, you change your code generation strategy, or when the generated code for a given class might depend on information from other classes. This shows up with, in Java with bridge methods all the time. So, you know, separate compilation can really, actually torpedo an otherwise worthwhile language feature. Now, this isn't to say that we never violate any of these kinds of compatibility, because after all, you can't fix a bug without breaking behavioral compatibility. And sometimes there are bugs we don't fix for this reason. But, sometimes after sufficiently quantifying the amount of, code we might break, we might consider whether it's the right thing to do, but not lightly. So a lot of people think that we're kind of crazy to be so rabid about compatibility, but really there isn't any other responsible choice, because if you have billions of lines of code out there, pretty much any incompatible code change is going to break someone's mission-critical code. And it takes a particular brand of arrogance to say, yeah, you should break his code, it's for his own good. We do get these suggestions a lot. And I'm sure these people think they're being helpful rather than arrogant, but the mistake is they're only focusing on part of the picture. So what I see is that developers tend to overestimate the importance of code and underestimate the importance of stable programs. And it's not too surprising, right? The developers look at code all day. So of course that's where their aesthetic center is, but you have to keep in mind that's only part of the picture, and there's a lot more to it than that. So just because you're constrained by compatibility doesn't mean it's impossible to evolve. It just means that the set of sensible evolutionary directions, is a little bit constrained. So I'll take a simple example from the Java 5.0 days when we added autoboxing to the language. So autoboxing is an implicit conversion between a primitive and its box reference form. Nice little feature, let the compiler figure out the conversion mechanics for you. Great, okay. But now we've got a problem with overload selection, because prior to Java 5, if you had two methods and you had this method call, only one of them was going to be applicable, and the overload was uniquely resolved, so that's great. But once you add an implicit conversion from int to integer, now this call site is ambiguous, because both methods are applicable. So if we didn't do anything else, adding this autoboxing would have introduced a source incompatibility, because call sites that previously used to uniquely resolve become ambiguous and won't compile. And this is the sort of thing that's really easy to miss when you're focusing on a localized view of the code rather than a global view of the code base. So seemingly harmless things like a little implicit type conversion always is going to ripple into method overload selection and type inference and all that. And so overload selection has a lot of detail, but the concept is straightforward enough. You take the type of the arguments, you figure out what those are, you search the class for applicable overloads, and of those you pick the most specific and hope there's just one. So what autoboxing did was increase the set of applicable methods. So to resolve the conflict, we sort of turn to an odd trade-off, which is we trade compatibility for more complexity. So to preserve compatibility, we say, let's adjust the overload resolution by proceeding in steps where the first step is do the old thing. And if the old thing fails, then you proceed to the later steps. And so we invented this concept of strictly applicable versus loosely applicable, where strictly applicable is the old rule. And you do that first, and if that wins, you're done. And otherwise, you then move on to the second step. And we did this trick again in Java 8 with the inheritance semantics when we added the ability to inherit behavior from interfaces. Whenever there's a conflict between inheriting from a superclass and a superinterface, we say, oh, the superclass is going to win. And we do this because this guarantees that any code that worked prior to Java 8 works exactly the same way after Java 8. Might not be what you would pick if you had a blank sheet of paper to work with, but it's a reasonable choice that balances the various constraints. So the trick here basically is you focus your evolutionary effort on imparting semantics to programs that previously didn't have any semantics. And then you define all the features this interacts with to give priority to the old interpretation. This is a pretty good trick as long as you use it sparingly. I mean, if we went out of control with this, we could have a 93-step overload resolution algorithm. That wouldn't be so good. But if you evolve conservatively, this trick generally works well enough. So there's a subtle irony to this accusation that we're obsessed with compatibility and that we should just have the guts to make an incompatible change. And I've been looking for a way for quite a while to illustrate this irony, and this is the best I've come up with so far. So this picture is Central Park. Now, by some estimates, the real estate value of Central Park is about $500 billion. This represents a dramatically unstable equilibrium in real estate development, right? Leaving $500 billion of real estate deliberately undeveloped doesn't happen by accident, and it doesn't stay that way by accident. So the rightmost border of the park is 59th Street. And as you could probably imagine, property on 59th Street is pretty darn valuable. I'm sure it's occurred to every single real estate developer ever that, wouldn't it be really cool if I could build a building on 60th Street? And of course, the coolness of this, to being able to break the sanctity of this "we don't build here" rule, relies on being the only one to be allowed to break that sanctity. Otherwise, our would-be clever developer would be very surprised and dismayed when, his brother-in-law built a building on 61st Street. So the value of Central Park and the dependent value of parkfront property exists solely because there's a collective discipline of "we don't build here," and a confidence that this discipline will be continued in the future. Once that confidence is in doubt, the whole system comes crashing down. And the only reason it even occurs to someone to build there is that no one's been allowed to do it before. Okay, so here's the strange analogy. Java remains the world's most popular programming platform precisely because we never have thrown our customers under the bus like this by breaking their code. Class files you compiled in 1995 still work today, and they'll still work in 2035. Breaking changes are like that building on 60th Street. It may seem expedient in the short run, but there's no such thing as just one exception, and the only reason people even think it's a good idea is we've never done it, so they've never seen the consequences of what happens. So people continue to trust Java because they trust that we're not going to devalue their investment, and you only get one chance to break that trust. So the bizarre consequence is the more discipline you have, the more you're going to get ridiculed for that discipline. I guess discipline has to be its own reward, like my dad always said. So here's a story from the evolution of Java that illustrates how the cost-benefit equations shift when you take into account existing developers and code. In the most recent version of Java, we finally added Lambda Expressions. Now, some of you might find that laughable. Should we wait a minute? Do we need to break? Okay. But this actually illustrates a lot of the challenges of stewarding a mature platform. So the concept of Lambda Expression is, obviously straightforward enough. The hard part is always, how do you interpret the notion of lambdas in such a way that fits into what's been done before? And so it doesn't look nailed on the side, doesn't blow your complexity budget, doesn't break existing code, doesn't require that 9 million users can't do their job until they go back for more training, and in a way that allows users to gradually migrate their code from the old way to the new way without having to do it all at once. So what starts out as a pretty simple seeming problem turns out to be riddled with a lot of soft constraints that have to be carefully balanced. And these are all various forms of compatibility, not just compatibility with code, but compatibility with existing mental models or attitudes or skill levels. Now, in a statically typed language, when you add a new expression, the obvious question is, what's the type of that expression? So we have to decide what the static type of a lambda is, and there's an obvious answer to this question, a function type. After all, nearly every language that has lambdas and has types has a notion of a function type, starting with the lambda calculus. So it turns out that this answer is obvious and wrong. When you start pulling on the function type string, you discover it raises a lot more questions than it solves in the context of Java. And I have a whole talk on this issue, so I'll just give you the highlights. When you design a language feature, you don't only get to design the part where it meets the programmer. You also have to design where it meets the compilation target. And users might claim, oh, I only care about the source code. I just want to be able to write the code I want to write. And they say that, until it doesn't work the way they want it to, right? So if you don't have a clean way to express the code in terms of the underlying computing substrate, you're going to have performance potholes and complexities and corner cases, and then the users will complain. So if you say the type of a lambda is a function type, you need a way to express that in the JVM, and that raises many questions like, what would a type signature look like in a class file? What would the bytecode be for invocation? Do we need a new bytecode for that? How do we create instances of functions? Do we need a new bytecode for that? How do we map variants in the Java type system to the VM? Now, the JVM doesn't have any native way to represent function types, so we'd have to invent one, which we could. We could add new type signatures and new bytecodes and new verification rules, which, of course, is expensive. Or we could simulate them with generics, which are erased, which would suck. So we could have these boxed erased function types, which is not what anybody wants. So, and the bottom line here is if you have a gap between the way the language represents a concept and the way the underlying representation in bytecode or wherever you compile to, this always causes problems. So instead, we backed off from the what would be the perfect way to do this perspective and doubled down on, well, how does Java do this already? Which turns out there was a good answer lurking there. We looked at how we abstract over behavior in Java without function types. And the way you do that is you write an interface with one method, like runnable or comparator or action listener, and you use that as the argument type of some method. Right? So you've all seen code like this, right? And if you ignore the syntactic pain of inner classes, which obviously you can't ignore, this works reasonably well. The parameter has an obvious type. It can represent primitives without boxing and references without erasure, so that's good. So you could call these things nominal function types. So in the end, we decided, let's just formalize the idiom by giving it a name. So one method interfaces are now called functional interfaces. And we define a conversion from a Lambda expression to a compatible functional interface type. And then we teach type inference to propagate information from the signature of the single method into the Lambda expression, which is not totally obvious from a type theory perspective, but in hindsight should have been the obvious thing to do just by looking at the code that Java developers actually write. So the bottom code is a lot better than the top code. We're pretty happy with the result. There was a lot of work that went into making type inference work this way, a lot of work under the hood. So doing this, saved a huge chunk of our complexity budget. So instead of introducing function types into the type system, which users would have to learn about, and then we have to specify and implement them in the compiler and the JVM, instead we just gave a name to an idiom that everyone already knew. And this enabled us to spend the complexity budget on better type inference. And which was where, like I said, almost all the work went into, overhauling the interaction between type inference and overload selection, which are features that are under the waterline, right? Most Java developers don't even know that they exist until they get a compiler error. So there were a lot of obvious but wrong choices that presented themselves during this evolutionary exercise. And I don't really have a lot of concrete advice for how to identify obvious from wrong from obvious and maybe right, except to be aware that they come along pretty frequently, and you have to be open to the subtle warning signs that suggest that the obvious choice might not be the one you want. And of course, no matter how much thought you put into it, you could still be wrong, right? I mean, the best that language and library designers can do is to move slowly and deliberately enough to minimize the impact of decisions that might be seen as mistakes in the future. But we could still be wrong. Java's alter statement is only one bad decision away. So it turned out that this decision to embrace nominal function types rather than structural ones paid this huge dividend that we didn't see from the outset. So pretend for a second that adding function types to Java turned out to be really easy. So we just rushed down that path without thinking about it, and then we pat ourselves on the back for having made Java so much better, right? Now, see what the ecosystem does. What happens when we release this new and improved Java? Well, remember, one of the assets of the ecosystem is the huge variety of libraries out there. If we introduced a better way to represent behavior in the type system, we immediately relegate all the existing libraries to doing it the old way. And now begins the 5 to 10 year churning process where library maintainers have to spend their effort maintaining both old way and new way libraries at the same time and migrate from old way to new way and suffer dependencies where you can't migrate because your dependencies haven't migrated. What a waste of time, right? These libraries are fine. And by picking an idiom that existing libraries already use to model behavior, we achieve this very rare kind of compatibility, which is forward compatibility with language features that didn't exist at the time the code was written. So all those old libraries that used this common idiom were already Lambda ready from the outset. So because doing real function types turned out to be hard, we kind of dodged a bullet in terms of the adoption and migration curve, which would have imposed billions of dollars of unnecessary cost onto the ecosystem. The choice not to do structural function types illustrates another lesson worth pointing out. If you don't know the right answer, at least don't do the wrong thing. And that sounds really easy to say, but it's actually really hard to do. We didn't know how to do structural function types in a way that met all our goals, expressiveness and performance and complexity and migration compatibility. So rather than press forward anyway, which was tempting, we had the discipline to leave it alone. And we did make a number of subtle decisions that left the door open to doing it in the future, such as explicitly disclaiming any meaning to the identity of the result of Lambda conversion. As it turns out, we think we figured out how to get there in the future, and we're pretty glad that we didn't do it wrong when we were under so much pressure. At the recent Java 1 in San Francisco, James Gosling told a similar story about why generics weren't included in Java from the beginning. It wasn't because parametric polymorphism wasn't understood in 1995. It wasn't because we thought it was a good idea to have a static type system that was so weak that you could put typed elements into a container and not retain their types when they came out. It wasn't, it was because we didn't know how to do it right. Some people might argue we still don't, but I think we're pretty glad that we didn't get C++ templates in 1995 or patterns from Beta. So it took longer than we'd hoped, but the generics we got were a lot closer to the spirit of the language, and the generics we would have gotten in 95 weren't. So if you don't know the right thing to do, at the very least, don't do the wrong thing. And sometimes that means doing nothing, and that's okay. It has to be okay. And the lesson here is reality hardens like concrete. Before you do anything, there's many possible potential paths ahead. Once you do something, there are many fewer, maybe just one. So it's true for little things as well as for big things. Always be aware of what doors you're closing implicitly with every decision you make. So okay, just in case you've not seen what Java 8 code looks like, let me just give you a quick peek. Here's a quick example. It's a typical filter map reduce operation on a collection. Okay, big deal. Java finally caught up with idioms that Python and Ruby and JavaScript have had for many, many years. Well, there is a big deal here, and the big deal is how we've integrated into the existing libraries. It's not just bolted on, it's not just skin deep. We've integrated parallelism into the model. Java always had good libraries for parallelism, but the sequential and parallel expression of a computation always looked very different. And that meant to go parallel, you had to rewrite your code and retest your code, and not anymore. Now you can just say, take the stream, make it a parallel stream, and the sequential and parallel code look almost identical. So there's a lot of power beneath the surface here, and that's where the power belongs. Here in this example, people is an ordinary collection. So all the collection implementations were retrofitted to support decomposability so that all collections can be sources for parallel streams. Similarly, all the stream operations like filter and map work off a general abstraction for element access and decomposition. So anybody's collections or other data sources like generator functions or queries can act as sources for stream pipelines. And it might look like, if you're used to reading Java code, this looks like 3 distinct operations, filtering, mapping, and reduction, but the library is lazy, so the operations get fused into a single pass on the data. So, and then, as a sort of last little bonus, the implementation tracks where the data came from and what its characteristics are. So if your source was, say, a tree set, and you filtered it and asked it to sort the elements, it would say, oh, I know the elements are already sorted, so I'll just do nothing there. So not only have we caught up with some other languages, other curly brace languages in expressiveness, we really blow them away in performance. Now, the imperative version of filter MapReduce isn't so terribly ugly either, right? But more complicated Java code tends to get ugly fast because there's so much accidental detail that leaks out, right? So, here's an example of your typical idiomatic Java code that does a query on a collection. Doesn't really matter what it does. The important part is you have to wade through too much detail to figure out what it does. So if you, rewrite this with the stream library in Java 8, it actually looks like the problem statement. And as you know, code that looks like the problem statement is more likely to be right. Now, I know I don't have to sell this audience on any of the benefits of this approach. My actual point here is it's possible to teach a 20-year-old language some surprising new tricks. You just have to be willing to work within the constraints. So Java 8 was a big upgrade, probably the biggest ever to the Java programming model. We had coordinated improvements to the language, VM, and libraries. Subjectively, 4 years ago, I think the dominant attitude in the community seemed to be, Java is done for. It's the new COBOL. It's had its day. Today, I'm seeing a very different attitude. There's a lot of excitement in the Java community about this new and improved Java. So coming off a success like this, it's about time for the second system effect to kick in, right? So what are we doing next, right? We're just going to sit on our laurels? No, of course not. We're going to do lots of cool things. So to start with, I think we've come to a much more sophisticated view of coevolution between the language and the JVM. Now, don't worry that the JVM is going to become increasingly beholden to the Java language. In fact, the opposite is true. But in the Java 5 days, when we added generics, it wasn't an option to do it in the VM. So everything had to be done with front-end compiler transformations. And this was doable, but it had some of those impedance mismatches that I talked about earlier that result in problems like bridge methods that poke their heads up every once in a while. So, since then, there's been a lot of consolidation in the JVM market. It's basically just Oracle and IBM in the server JVM market, which makes it a lot more practical to evolve the JVM if there's reason to do so. It's a lot easier to get 2 big companies to agree on something than 12. So our approach for evolving the platform is a practical one. We try to find the biggest pain points and hammer on those. And for Java 8, the pain points are mostly language-driven, improving the ability to abstract over behavior. But pain points are sometimes hardware-driven, too. And we want Java and the JVM to perform well on basically the moving target of modern hardware, for whatever that means at a given day. So for any given feature, we often have a choice of where do we implement it. Do we do it in the library, in the front-end compiler, or the VM? Now, language development is slower and more expensive than library development. VM development, even more so. But there's often a right place to put a feature. And when it comes to hardware-driven features, very often the only choice is in the VM. So language VM coevolution means finding the balance between these 2 opposing forces. On the one hand, we want to keep Java language complexity out of the VM. On the other hand, we want the mapping between source code and bytecode to be straightforward and to be free of impedance mismatches. So the Java 1.0 design leaned really hard towards the latter. Java 1.0 is basically an assembler for the JVM instruction set. But the cost of this was we burned way too much about the Java language and the Java object model into bytecodes like invoke virtual that understood the Java semantics of method inheritance and linkage. So over the years, we've been hammering at places where the VM instruction set is too Java-specific, like the invoke dynamic bytecode we added in 7, and this allows non-Java compilers to efficiently encode language-specific semantics in the VM in a way that the VM can see through and therefore optimize. Now, Java 5 leaned a little too hard in the other direction by doing everything in the front-end compiler, which increased the semantic gap between the language and the bytecode, and that created complexity in corner cases. So that might be too little VM involvement, but we also could have made the mistake of going in the other direction. In fact, one of the persistent calls for fixing something that's broken about Java is that we should reify generics. Now, when pressed, most developers can't tell us exactly why they hate erasure so much. If you ask them, the usual answer is some permutation of, "'cause it sucks." But a naive interpretation of reifying generics would mean pushing the generic type system, including wildcards, into the JVM. So how many of you here think would be a great idea if the bytecode generated by the Clojure compiler not only had to satisfy the Java generic type system, but you also had to pay for the potentially undecidable generic subtyping checks at runtime on every array store? Good idea, right? Yeah, thought so. So the winning move here, of course, is to pull a rabbit out of your hat, right? You have to factor a feature into a set of sensible language-agnostic VM primitives that can be used by a front-end compiler. So in Java 8, we had a nice illustration of this. I remember the bit about converting Lambda expressions to one-method interfaces. So you need a way to take a Lambda body and its carried arguments and convert it to an instance of a compatible interface. So we could, of course, just have the compiler spin classes for this, and that's what the prototype actually did. But instead what we did was build on invoke dynamic to expose a VM optimizable implementation of Lambda conversion. And we stuck this in the platform runtime with a good specification so any compiler could use it. And in fact, Scala will be using it in 2.12 for their Lambdas, which means any optimization work we do in the core platform accrues to their code as well without any changes or, well, theoretically without having to recompile your code, but that's not really an option for Scala developers most of the time. But we like it. Okay, so I talked about tracking changes in the hardware. Hardware certainly has evolved a lot over 25 years. You know, in the ancient days, you had these single core, single socket systems with no cache, no instruction level parallelism, no pipelining. And in these days, an arithmetic operation and a memory fetch cost about the same thing. So the performance model was really simple. Basically, you counted instructions. And over time, systems got more complicated. We added cache. We added multiple levels of cache. We added multiple cores on a chip. We added lots of cores on a chip. We added multiple sockets. And, you know, these systems got more sophisticated, and as a result, memory access became more expensive and less predictable. So memory access could cost you as little as a few cycles or as much as a few hundred cycles, depending on where the data is served out of. And at the same time, cores got fancier and more complicated with deep pipelines and superscalar execution. So if a cache miss cost you 300 clock cycles and you can issue 4 instructions per cycle, a cache miss may cost you 1,000 arithmetic operations. That's obviously a worst case, but that's a big deal. So it stands to reason that whatever trade-offs we made in 1995 about laying out data in memory can't possibly be optimal for today's systems. So what does the JVM type system give you? You've got 8 primitive types. You've got heterogeneous aggregates with identity, classes, and homogeneous aggregates with identity, arrays. Now, this is super flexible, right? You can model anything you want with it, and we do. But the big problem is it's hard to get away from object identity unless you can fit your data in perfectly in one of those 8 primitive data types. Now, what is identity for? It exists to serve mutability and polymorphism. Not all objects need this, but all objects pay for it. And you might think the VM might just figure it out. I mean, JVMs have gotten really good at slicing through the cost of code abstraction, but they never really got very good at slicing through data abstraction, because the VM can't really figure out when an object is going to need its identity unless it can see all the way from the allocation to where it goes out of scope. And so the VM has to be pessimistic in how it lays out data. So imagine you've got, you know, a simple tuple class like point, got an x and a y field, and let's say it's immutable and final, so it can't be polymorphic and it doesn't really need object identity. But you get fries with your order whether you wanted them or not. So you got an array of these things. How does it get laid out? Well, the array has an object header, and each element of the array is a reference to a point object, which has its own block of memory and its own object header. And from a memory efficiency perspective, we're not doing so well, right? We have 2 words of header plus a pointer for 2 words of data. So that's a big overhead. And because these objects are heap allocated, that's work for the allocator and the garbage collector. But the real cost, it comes from the indirections of all those pointers. And if you've got an array of plain old ints, you get great locality when you traverse the array, because you pull in one int and it pulls like the next 7 or 15 into L1 with it. And then like when you go read the second one, it's already pulling in the next block of them because it's predicting what you're going to do. And that works really well. On the other hand, if you've got an array of objects, like in this picture, you get pretty decent locality fetching the pointers, but then you're probably going to cache miss on every one of those dereferences. So remember that 1000x penalty for cache missing? Oops. And it's not even a deterministic penalty, right? So you pay in performance and you pay in predictability. Now, sometimes this doesn't matter. You might have a small data set. You may meet your performance requirements with plenty to spare. But if you're doing high-frequency trading or big data, this cost counts a lot. And you didn't ask for this layout. It's just what you'd really rather have is this layout, right? So when confronted with a situation like this, developers often take matters into their own hands. And sometimes they have to, and sometimes they just can't help themselves. So developers will do silly things like, shredding an array of points into 2 arrays of primitives, hoping to regain the locality that they lost in object layout. And of course, this code's harder to read, harder to write, harder to maintain, more error prone. And the sad part is developers often do stupid things like this for performance reasons with no actual evidence that their code doesn't meet its performance requirements, or in fact without even having performance requirements or metrics in hand. But regardless of whether developers do this out of genuine need or some destructive obsessive compulsive disorder, it doesn't really matter, right? We have to stop putting developers in a position where they have to choose between getting good abstraction and getting good performance. So this brings us to a VM feature I think you're going to like, value types. Now, I know I don't have to sell this crowd on the value of values, but having VM support for values would be really nice. And if we recast our point class as a value, what we're saying is we don't care about identity and all the stuff that brings with it. And by giving up on that bit of flexibility, we gain the ability for the VM to treat an aggregate like an XY point as a value. So values are implicitly immutable and final, and they derive equality from their state rather than identity, and they can be passed, well, by value in registers or on the stack instead of in heap nodes. And they can also be flattened into arrays and inlined into other objects. So values can actually have most of the things that classes can have. They can have methods and constructors and fields, and their methods can be public or private, and they can use generics. And because values are monomorphic, there's no dispatch cost for invoking the method of a value type. They act just like static methods. So basically, our mantra here for value types is codes like a class, behaves like an int. So the applications for this are obvious, right? Numerics, tuples, algebraic data types like optional, STL-style cursors instead of mutable iterators like Java has. And because value types can encapsulate data just like reference classes, values can act as secure but cost-free wrappers around sensitive data, such as internal references or native pointers, and they mediate access to the data and provide type safety without adding an extra level of cost. So you get safety, encapsulation, and performance. Free lunch, woo! So since this affects data layout, it means it has to be a VM feature first and a language feature second, but the language support for it will be a pretty straightforward mapping to the VM feature the way we like it. So I bet that non-Java languages will actually benefit from this way more than we will, because non-Java languages have to express their internal data structures using Java, and so they're paying all the penalties of this kind of layout. So even if none of you ever directly program in Java with this, you're all going to benefit from it tremendously. So when you look at generics with boxed primitives, you see all the same layout problems that you see with arrays. Inefficient data layout, too much indirection, loss of locality, too much allocation. And so if we're adding value types, we have to look at how does this interact with, with existing features, like generics. So if you have an array list, of integers, it's going to be represented by an object that's going to point to an array. Each array is going to point to a boxed integer. Yuck. So from a Java language perspective, once you add values, you immediately see that the uneasy truce we made in 2004, where you can generify over references but not primitives, starts to fall apart. So when there were only 8 primitive types, we were kind of willing to look the other way, but once you add user-definable primitives, it really has to work with generics. So we're going to have to bite the bullet and support generics over primitives and values, so you can say list of int instead of list of integer, and have under the covers have it actually point to an array of ints. This will be accomplished by on-the-fly bytecode transformation, so you get deep specialization like this. And again, if you're not Java programmers, you may not be as interested in the details, but you're going to be very interested in the mechanism. I think Gotti talked about this a little bit on Thursday. So recall earlier when I was talking about looking for language-agnostic building blocks that the VM can provide to compilers. And one of the interesting building blocks is the ability to describe a class not by name, but by recipe. So at the bytecode level, this array list of int class will actually be written in some encoding of the class resulting from applying the specialization transform to an array list with argument t equal int. And once you have that mechanism for describing a class by pattern instantiation instead of by name, this trick can immediately be used for lots of other things: proxy classes, tuple classes, adapter classes, etc. And again, this is something that's a compiler writer's dream, right? Things that you would have to generate statically or play games with class loaders, you can generate actually within the VM class definition model. So in case anybody's interested in getting involved, these features are all being developed in OpenJDK under 2 projects, Valhalla and Panama. So the first is about value types and specialized generics, like I've talked about. The latter is about better interop with native code and access to native data on the native heap. And together, these are sort of a comprehensive story for more flexible and efficient access to data in memory, better data layout, direct access to data in native memory, more flexible arrays, and a unified, safe, and fast API for exotic access to variables like fenced and atomic access, whether they're stored in fields or arrays or even off heap. So these are all like JVM features first and language features second, and most of these will probably find some use in Clojure to improve footprint and performance. So it's a really cool time to be involved in JVM evolution. So, okay, it's getting to be time to wrap up. So I'll just close with a little bit of a warning. Be careful what you ask for. We all want the software we write to be successful, but success brings with it some cost and constraints that can be really frustrating at times. On the other hand, these constraints, most notably keeping the promises that you made to your users, whether you made them implicitly or explicitly, forces you to spend time up front thinking about whether something is the right thing to do, the best use of your resources, what the possible consequences and the possible interactions might be. And most of the time, thinking deeply about what you're going to do ahead of time really pays off, even if it means you can't rush forward as quickly as you might otherwise want to. And I think these are issues that the Clojure community may soon be facing, if you're lucky. So suit up. And, oh, almost forgot the pony. Thank you, everybody, for listening. So, do we have time for questions? I'm happy to do questions. Yeah, we'll take 5 minutes for questions. Right there.
What's your idea about Scala versus Java 8?
So the question is, what's my idea about Scala versus Java 8? So I think Scala is great. Scala is able to do experiments that we don't have the luxury of doing. And they're going to do some things that are successful and some things that are unsuccessful. And we can learn from both of those things. And there's a lot that we can learn from the experiments Scala have done, and then we can steal the good bits. I think it's great to have, have them in the ecosystem. I do think a lot of Java developers who left Java because it was too painful are now taking a backwards look and saying, hey, maybe it's getting better over there. And we are seeing a lot of big sites move from Java to Scala and are moving back. But yeah, no, I think it's great, and I think it's very interesting to see some of the consequences of the decision they're making, and that may have looked like obvious choices at the time, and then in hindsight may look like they were mistakes. And it's good for someone else to be making those mistakes for us. I won't predict the future. The question is, will Scala survive? I don't know. I hope it does. I don't know. Other questions? Over here. Yeah, so the question is, okay, you made the decision not to push generics into the JVM in 2004, which was really the time we had a chance to do that. And having sort of missed that boat, can that ever be revisited, or are there other things that we can do? Is that basically your question? So, we've spent a lot of time thinking about, is it practical to do reified generics? And the conclusion that we mostly come to is, well, I think people think they want it for the wrong reasons. The compatibility costs are devastating. I mean, if you look at what C# went through, they only were able to get away with it because they did it at a time before they had any users, which is great if you have that chance, but if you miss that boat, you've missed it. The pain points of erasure, I think, can be solved without reification. So one of the biggest pain points, for example, is it's really hard to write serialization and deserialization libraries that convert objects to XML and back. But a lot of that pain can be addressed by better type literals without having to go all the way down to reifying generics in the VM. So I think there are easier paths to getting there that don't involve upsetting the whole world. All right, a couple more questions. This guy had his hand up before. Go ahead. Yeah, you. The question is, can you think of a decision that you wish you could have made the other way? I'll give you a good example. This wasn't a decision that I made personally, but I know the people who made this decision feel this way about it. So when we added autoboxing to Java and Java 5, we defined equality by identity rather than by value. That seemed like the compatible thing to do at the time. It turned out to be a dumb thing to do. We would have all been way better off if we defined equality on boxed integers by value instead of by reference. But I think it was one of those things where it just seemed like an obvious choice, and it wasn't hard, so we went with it, and then after the fact realized, that we had kind of painted ourselves into a corner. It's not a dramatic example, but I think the people involved all agree that should have gone the other way on that one. Over there. So the question is, you were dumping on serialization before, so obviously there were some big mistakes made with serialization. What did we learn from that? Is that your question? Yeah. So serialization is a really tough one because on the one hand, as a language feature, it made every possible mistake in the book, right? It wasn't integrated into the object model. It was this weird thing nailed onto the side. It is horribly insecure. It's horribly non-transparent. It uses magic methods. It violates basically every principle of object-oriented design. And yet, I think if it hadn't been for serialization, which is the basis for easy remoting, Java might not have been where it is today because the success of Java, I think, had a lot to do in the late 90s with how easy it was to build distributed object frameworks. And so on the one hand, I really regret everything about serialization. On the other hand, I think Java would be in a dramatically different and worse position now had we not done it that way. So I think the idea is okay, but the magicness of it isn't. And I sort of understand the rationale for a lot of the decisions. Some of the decisions were just boneheaded and were rammed through under time pressure. But I think the attempt to be magic was the big mistake. All right, I think we have time for one more question. So the question is, people are much more aware of functional programming as a paradigm than they were in the past, and is the JVM evolving towards that? So I think the answer is yes. But the way I look at it is, the choice between object-oriented programming and functional programming is not an either-or, right? Object-oriented programming is one way of modeling the world. It's fairly good at modeling abstraction over data. Functional programming is another way of modeling a world, and it's very good at abstracting over behavior. And most programs have both. So the way I like to look at it is you should learn classical object-oriented programming and you should learn classical functional programming, and then you should think about how am I going to use these concepts to help me write the program in front of me better, drawing from both of those. But I think to answer your question, I think there are a lot of pieces that the VM could pick up fairly easily. One of the constant calls for is tail recursion. It turns out that the reason the JVM doesn't do tail recursion is for a very stupid reason. And it's only one that we've recently been able to move a step forward in. So it turned out in the implementation of JDK classes, not for any good reason, but because this is how the world is, there are a number of security-sensitive methods that rely on counting stack frames between JDK library code and the calling code to figure out who's calling them, which is a horrible, brittle way to do it, but it was an expedient thing to do in 1995. And we recently replaced that with a mechanism to be a lot more robust and to get rid of the nasty frame counting stuff. But that made any kind of tail recursion a no-go, because it meant anything that mucked with the number of frames between the nominal caller and the nominal destination was a security error. So we actually, in the last 2 or 3 years, have removed what is actually the biggest impediment to doing tail recursion in the VM. It's on the radar. It's not the highest priority, but it will eventually get done. All right, thank you very much.